Hi, this is Chapter 15, Part B, Electrodes and Potentiometry from Harris's Quantitative Chemical Analysis, 9th edition. In the first part of this chapter lecture video series, I discussed the use of reference electrodes and then converting between scales from reference electrodes. In this video, we'll actually cover the remaining learning objectives in part or completely, including a brief discussion of indicator electrodes and trying to identify them. There are two main types that we'll briefly discuss. We'll talk about how they're used. We'll solve for a couple of relevant quantities and define some terms as we go. And we'll be able to take a look at some reference electrodes and understand their architecture and how they're built. So first we need to understand this term junction potential. And a junction potential is a potential that develops at an interface because some ions have greater mobility than others. And so a potential, remember, is the separation of charge. And as I was saying, it develops at the interface between two dissimilar electrolyte solutions. And across that phase boundary, or that boundary between them, we can see that because some ions will move faster than others, in this case we have the greater mobility of chloride above and the lower mobility of the sodium. And so we'll build up a partial negative charge on the right and a partial positive charge on the left. And those charges and their separation are really the basic definition of a potential. So we can build up this junction potential. Well, as it turns out, it leads to uncertainty in the measure that we make in potentiometric systems. So in these types of systems where we're trying to measure potential, whether that be for a circuit or across a particular distance, it's going to lead to error in that because it's a portion of the system that we may need to account for but may have a difficult time doing. It also, as it turns out, you can imagine would oppose further charge transfer through that boundary, since we're going to be creating a positive partial charge on the left side. Any more chloride ions that approach that from the sodium chloride solution on the left are going to have a difficult time making it through and into the water. And so we can actually see a slowing of the transfer of the charge as a result of the junction potential buildup. But it does not disrupt bulk electroneutrality, since it's just a small region that only exists a couple of nanometers really on either side of that surface boundary. You can see here on the right-hand side we have a table of mobilities. It's reference values that you would, of course, be provided either via table or in any problem that we're going to try to solve. And these describe the mobility of the ions across these boundaries, and so we want to be able to come back to this table when needed. Now, there are two types of indicator electrodes, and these are different from reference electrodes. The reference electrodes that we've already talked about involve redox chemistry, where indicator electrodes do not include that. The first type of indicator electrode is just a metal wire, so metal indicator electrodes. These are made from inert metals. They're placed into solution, and if you think about the types of galvanic cells that we've already studied, these are the electrodes that are used when both of the chemical species for a half cell are soluble. Neither of them are a conducting material. So in the case of Fe3+ and Fe2+, neither of those iron ions can be used to make the electrode. And so the electrode that completes the circuit into solution must be some other material. Platinum is a very good material for this. Gold is a very good material for this. Silver can be used at times. These are relatively inert. They don't oxidize, especially gold and platinum. They don't oxidize readily, and so they stand up to the sorts of solution conditions that we have when we're doing electrochemistry. And so the other type of indicator electrode is actually ion selective electrode. And these are electrodes that have a particular ion that they're able to measure the concentration of, because they have been designed in such a way to only measure the potential difference across a membrane of that ion being transferred. So they respond to one ion, they do not directly involve redox chemistry, and they measure the concentration of some ion, we'll just say A. In fact, in the illustration on the right, we are able to measure the concentration of A- as the mobile ion C+ can be transferred through the ion selective membrane. And we're able to measure then that concentration without allowing the analyte to be transferred through the membrane and thus reducing the actual concentration or contaminating the ion selective electrode solution. So as I said, only C+ can pass through. We can observe it both in the outer solution within the membrane and then also within the filling solution of the filling solution of the ion selective electrode, and therefore the junction potential Jp is proportional to the concentration of C+, and from that we can calculate values for A-. So when we measure a junction potential, we have an equation that I've listed below that we'll discuss, but first I want to draw an illustration of an ion selective electrode. We of course have our electrode body, we have a membrane drawn at the bottom, and then over time we build up that junction potential where we have a negative charge on one side and a positive charge on the other. We just arbitrarily assign those for now because they're dependent on the particular ion selective electrode. We have the inner solution and the outer solution. And then we have the potential from the equation below that we measure across the membrane, that's E. It's equal to a constant plus 0.05916 over n times the log of A. If you think about it, this equation is very similar to another equation we've used, that being the Nernst equation. And so the equation helps us understand this because we can see that for every factor of 10 in concentration change, the change in the total potential is equal to 59.16 millivolts. We know that N is equal to the charge of the analyte. So for instance, for a proton, if we were measuring that, N would be equal to 1. And A0 is equal to the activity of the unknown solution. So we're looking for these values, and we can solve then for the electric potential across that, or we can measure, in the case where we're using the ion selective electrode to measure concentration, we can measure the potential, and then via this equation we can solve for activity and back calculate our concentration. Of course, ion selective electrodes do have some inherent advantages and disadvantages. And so advantages are they respond linearly to the log of the analyte activity. We just described that in terms of their growth in terms of potential by the 59 millivolts per decade of concentration. The sample is not destroyed during the measurement, so they're a non-destructive technique. They cause negligible contamination. They're fairly short response time. They perform well in colored or turbid solutions, so cloudy and colored solutions, where other techniques like UV vis may not be able to transmit light well. These systems can work very well, and they're quite portable. In fact, some of them are handheld about the size of a pen. Precision is usually less than 1% is a disadvantage, and so without careful design, you're not going to get the same levels of precision you can get from other techniques. They're easily fouled by proteins and organic solutes if the matrix is very complex or biological. So they need to be cleaned and cared for well. They're fragile. The membrane can be broken easily. They have a limited shelf life, so even if you don't break your membrane, you are likely to have to replace it over time and to continue to replace them periodically. The response is temperature dependent, and so we know from the Nernst equation, when we don't simplify it for 25 degrees C, there is a temperature component in there, and we would see that again in this equation. And then they require frequent calibration, typically done daily or even more in heavy use situations. So let's take a look at one specifically. A pH glass electrode is considered an ion selective electrode. Of course, we know that it selects for the H+ ion and it does not measure the concentration of other ions. So how is it built? Well, this is the most common type of ion selective electrode. It's a combination electrode, which includes an outer reference electrode that's a silver-silver chloride electrode. It includes the membrane. It includes the filling solution, and then an inner reference electrode, which is again a silver-silver chloride electrode. And we can see then, sandwiched in there next to the salt bridge, is the analyte, H plus aqueous, and that is separated from the filling solution H plus by the glass membrane. And then there's a charge buildup on each side, and that separation of charge, the separation maintained by the glass membrane and by the fact that H plus does not travel freely through the glass membrane, we can measure based on the separation of charge, that potential, what the concentration is. So the only dynamic value in this system is actually that single analyte concentration, H plus ion. You can see in the architecture, if you compare the line diagram with the illustration, you can pick out things like the silver wire, the silver chloride paste. You can see that there's a salt bridge, which they just have labeled as a porous plug. This allows transfer between the two solutions. You can also see the glass membrane is labeled. We have things saturated with silver chloride to make sure that chloride ion is not changing over time. And then you can use this electrode, as you have much experience with, to measure the concentration of H plus ions in solution. So how does it work? Let's take a little bit closer look here quickly. We can see here that we have the internal solution on the left on the illustration above, and then we have the external solution, which has a variable activity of H plus ion. We can see that we have an outer layer of the glass membrane, about 10 nanometers, that's hydrated. And so we need to keep these ion selective electrodes in hydrating fluid. Usually we use a salt solution to maintain the ion density within the glass layer also. So we keep them in these solutions when we're not using them. We try to not allow them to dry out. And then we can see in the illustration below that on the surface of that glass we have O- sites, because again this is silica, this is a glass material, so SiO2. So there's plenty of oxides on the surface of the glass. Those oxides interact with the H+, they bind that H+, and we can see that on the internal solution that'll be fairly constant. We know what that amount of H+ bound to the O- is, but on the outside of the glass surface that's going to vary over time. And so depending on the concentration of H+, we're going to see varying amounts of H+ actually bound there. Now that separation of charge, the separation again maintained by the glass, is measured by the electrode, and we can then correlate that from the equation for junction potential to the concentration of H+ ion in solution. Okay, so let's draw another illustration. This is our own. So we've got the glass membrane. Again, on the left, I'm going to put inner solution, then the membrane, and then the outer, along with the two hydrated layers. Then on the left, I have 0.1 molar H+ ion in salt that's saturated with chloride to keep that constant. And of course, we have the positive charged ions, and we have negatively charged ions. We know that we have H+, but we also have sodium+, because that's actually the source of the saturated chloride along with Ag+. Sodium can move through the glass membrane. And then on the outside, in our solution, we have H+ ions at a concentration that is dictated by the pH of our solution. So as H+ approaches the gel layer, it forces the sodiums out of their bound sites with the oxides. They can then transfer into the glass membrane, or in some cases, if they're close enough to the surface, they can transfer out of it. But they're replaced by H+ because H+ is more tightly bound. Then we see a buildup as this happens. We see a buildup of potential on the outer hydrated layer, we see a buildup of potential in the inner hydrated layer. And the total membrane potential then is the difference between the outer potential and the inner potential. And this is actually used to calculate the concentration of H plus outside. So here's an equation for this. The equation we already saw, E is equal to a constant plus 0.05916 over N times the log of the activity of our analyte. Well, if we solve this for our pH glass electrode, we end up with E is equal to a constant minus 0.05916 times the pH. Well, the sign change that you notice between the two of them is because its pH is the negative log of H plus ion concentration. So that negative log works its way through. Of course, N is equal to positive 1, and so we can simplify the equation quite a lot. And then we know that the log of activity is going to be proportional to the pH, where activity is equal to gamma of H plus times the concentration of H plus. And so oftentimes we omit the fact that it's activity we're measuring, and we just assume it's actual concentration. Though now in analytical chemistry we've learned that this is not always a good assumption. So using this equation, we see that the voltage of the pH electrode changes, as I said, by 59.16 millivolts for every pH unit, which is a decade of H plus ion concentrations. So the question that we're left with is, why is this helpful? Because it is. So think for just a moment and see if you can come up with a reason for the benefit of this. As it turns out, the benefit of this being linear and of having a known increase, a known slope of the line, is that we can actually do a calibration of our pH ion selective electrode with just 2 data points. You've probably done this quite a few times already using our pH probes, and you'll notice that we only ever pull out 2 pH buffers that are calibrated to a particular value. And so from those we're able to calibrate the entire line, and we're actually able to trust that the other pHs are being measured quite well. So there are some errors in our pH measurements, even though it's a simple system. So for instance, our pH cannot be measured more accurately than our standards that we use, which are typically about calibrated to about 1/100th of a pH unit. So that's the extent of the quality of our measurement on a pH probe. For very, very basic pHs, electrode responds to Na plus, not H plus, since there's not enough H plus, and the apparent pH that one measures with the probe is lower than the true pH, and we call this sodium error, because sodium can actually build up that junction potential in the absence of ample H plus. Also, for very low pHs, all binding sites of O8, of O minus, all the oxides on the surface of the glass, can be occupied by H plus. And so there may be more H plus that's available, but it cannot occur at the surface because the pH is too low. And so this is called an acid error, where the solution is so acidic that we actually can't get an accurate measurement of all of the H plus ions. So pH probes are limited in terms of how good they are, how precise they are at measuring accuracy of measuring values, so how close they are to the true value. As we get to the extreme ends, say below pH 1 and above pH 13 would be issues for us. So these are some of the common errors. These are indicator electrodes, remembering 2 main types, metal electrodes and ion selective electrodes. And then, of course, the pH electrode is a very specific type of ion selectrode that we want to keep in mind and be familiar with.